for it. All right, so this one I got pin distance sets using effective dimension Stull. I got it right.
All right, thank
No
you.
help from you.
Okay, so thank you very much to the organizers. So in this talk, so in the last 5 years or so, been discovered that algorithmic randomness and effective methods can actually be used to make progress on some problems in classical geometric measure theory. And in particular, we're talking about proving theorems that don't have any computability in the statements, but in the proofs, we go through the effective domains that actually proving things. And this talk is going to be on a particular instance of this, a very recent application of effective dimension to something called pin distance sets. So I think I'll first start off with some background on Kolmogorov complexity and algorithmic randomness, and then tell you about pin distance sets, and then get into kind of a high-level overview of some of the ideas. Okay, so the principal definition we're going to be using to define algorithmic randomness is Kolmogorov complexity. So we'll be talking about the Kolmogorov complexity of real points, so Euclidean points. So we're going to fix a universal Turing machine U. We're going to let n and r be natural numbers and x be a point in Rn. We say that the Kolmogorov complexity of x at precision r, denoted case of r of x, this is the length of the shortest input pi, which causes this universal machine to eventually halt and output x. So this, if you've seen Kolmogorov complexity before, kr of x is the Kolmogorov complexity of dx, where dx is the closest dyadic rational at precision r to x. Okay. If you haven't seen this before, another shorthand for this is just the minimum number of bits to specify x to precision 2 to the negative r. So what's the shortest number of bits I can describe x in? It will also be useful to have a definition of conditional complexity. So the Kolmogorov complexity of x at precision r, given some other point y at precision t, is the length of the shortest input pi, which causes the universal machine to output this dyadic rational dx, if the universal machine is given pi and dy, which is the closest dyadic rational at precision t to y. So in other words, okay, so this should have a vertical bar, so it should be krx given y, sorry. But this is really quantifying the minimum number of bits to specify x to precision 2 to the negative r if you already know y. So you have y for free. How difficult is it to specify x to a certain precision? So there's a couple of properties, basic properties that we need. So for the first is, if you have any Euclidean point and any precision, the Kolmogorov complexity of that point is positive. It's greater than or equal to 0. And it's also upper bounded by n times r, plus this additive logarithmic term. Okay, so this upper bound just follows from the fact that in the worst case, if you need to specify x to precision 2 to the negative r, you just give the dyadic rational, kind of encode that into a binary string of length n times r. The second property that is used essentially in every proof at some point or another is the symmetry of information. So if you have 2 points, x and y, they don't have to necessarily live in the same space. But if you have 2 points, x and y, and 2 precision parameters, r and t, the complexity of the pair, x, y, is equal to the complexity of y at precision t plus the complexity of x given y, precision r. So if you haven't seen Kolmogorov complexity before, but you are familiar with Shannon entropy, it's basically the same thing. It's the symmetry of information for entropy, and it's almost the exact same.
Just to double check that. Faulkners R plus T.
The log of R plus C.
Yes.
Mhm, yeah. And really, it's kind of choose the max, and it's the log of that. Okay. The last thing that we'll need is just you can relativize all these definitions. Okay, so just take the underlying universal machine to be an oracle machine, and you can relativize everything we've seen to an arbitrary oracle plane. Okay.
Just double check.
Yeah.
N and M are fixed values that don't, the constant needed by the big O notation used.
It's gonna depend on N and M, and it's also gonna be dependent on the length of the vectors X and Y. So it's not really gonna depend on X and Y, but if, for example, X and Y are very far away from the origin, that's gonna be hidden in the constant somewhere. But in practice, we'll just pretend like everything is in the unit square. So we don't care about this. Yeah. Okay.
So sorry, what was the R and T? One was like. The second one, so T is what you need from Y.
Yes.
Get R.
So this quantity on the left is how difficult is it to describe X to precision 2 to the negative R and Y to precision 2 to the negative T.
Okay.
And it's the same thing as first describing Y to precision 2 to the negative T and then getting the conditional, describing X to 2 to the negative R given one. Okay. So once we have the notion of Kolmogorov complexity, we want to give some notion of randomness of Euclidean points. We can't really take the limits because they're not going to exist, but we can take the limit inferior and limit superior. And if you do this, you get notions of the effective Hausdorff dimension of a point, and then its dual, the effective strong dimension of the point. So these were originally defined by Jack Lutz and by Atreda et al. Using something called Gale's betting strategies. We're going to take these characterizations as definitions. Okay, so these are measuring the density of algorithmic information or density of algorithmic randomness of a point. Okay. And so the reason these things are useful in studying problems in classical mathematics is this point to set principle, which was proved by Jack and Neil Lutz around 2016. So it says that for any subset of the Euclidean space, the Hausdorff dimension is equal to the minimum over all oracles of the supremum of all points in your set of the effective dimension of X relative to A. And then the packing dimension is the same thing, except we use effective strong dimension. So I'm not going to give you the classical definitions of Hausdorff for packing dimension. I will just say that they are the most widely used notions of size or small or irregular sets. So these are just notions of size that quantify sets of measure 0, and using relativization and effective dimension, we can give a pointwise characterization of these two notions. So this bridge, the point to set principle, allows us to use techniques from algorithmic randomness and make progress on questions in geometric measurement. Okay. So that is a quick recap of the ideas from algorithmic randomness. Now I wanted to talk to you about the specific problem of my lecture today. So given a subset of Rn, the distance set is the set of all distances between pairs in your set. Take any pair X, Y in your set, measure the distance. That's the distance set. And then more generally, the pin distance set of E with respect to a point in Rn is just the set of distances from points in the set to X. And the main question we want, very natural question you would ask, is how do the sizes of the distance set and the pin distance set relate to the size of E? And intuitively, we think the larger E is, the larger the distance set should be. So for finite sets, this is a really famous old problem by Erdős, who conjectured that the size of the distance set is nearly linear in terms of the size of E. A pretty recent breakthrough paper by Guth and Katz proved this in the plane. So in R2, Guth and Katz more or less solve this, I think up to a logarithmic term. But this is still a really important problem in the finite case for higher dimensions, so for dimensions greater than 2. So Faulkner posed an analogous question when E is infinite, which is now known in geometric measure theory as Faulkner's distance set problem. And so in this case, we don't measure the measuring stick that we use to measure the size of E is Housework Dimension. And so Faulkner conjectured that if E has Housework Dimension strictly greater than n/2, where n is the ambient space, then the distance set of E has positive measure. This is still open in all dimensions, including 2. The best known bounds here are when the Housework dimension of a planar set has dimension strictly greater than 5/4, then the distance set has positive Lebesgue measure. Yeah.
Finite case. I mean, what's going on? Are these ones chosen in plane, say,
Yeah, just take endpoints in the plane.
generically?
The minimum. Yeah, so you know, an evil genius places endpoints in the plane. What's the size of what's the lower bound on the size of the distance set?
Makes not more sense.
Yeah. Mhm.
Okay.
Yeah. I mean, if you just randomly throw them on there, it'll probably be like n squared.
But also then doesn't Faulkner's conjecture because the Erdős conjecture is small, Faulkner conjecture says that the difference has to be big.
Erdős is the lower bound is at least linear, but you know it takes a lot of work even to do that.
That's just lower than that.
Yeah, the lower bound. Yeah, sorry. Erdős conjectured that the distance set has size at least linear in terms of size of the set.
Okay.
And Faulkner is doing basically the same thing, that if your set has Housework dimension at least n/2, then the distance set is very large. It has positive measure.
He's actually, that's fine. Supposed to be much stronger than lower bound than Faulkner suggested.
Yeah, I guess with the positive measure, yeah, it's
Okay.
okay. Yeah, so it is strong and it's still unknown. So there are many ways you can many variants of this question you can try to look at. And the one we'll focus on today is the variant where we talk about the Hausdorff dimension of pin distance sets in the plane. So we're going to restrict ourselves to the plane, and now we're going to look at the Hausdorff dimension of the pin distance. So Orpinen proved that if E is alpha is regular, which is some strong regularity condition on the set, of E is alpha is regular, and the Hausdorff dimension of E is strictly greater than 1, then for most points in the plane, the Hausdorff dimension of the pin distance set is equal to 1. It's the most it can be. Okay. Schmerken weakened the regularity assumption of Orpinen to just simple regularity, meaning that the Hausdorff and packing dimensions agree. We showed that if the Hausdorff dimension of E is equal to S, where S is somewhere between 1 and 5/4, then for most points X, the Hausdorff dimension of the pin distance set is at least 4/3 times the dimension minus 2/3. Schmerken later improved this bound for small values of S. So when S is somewhere between 1 and 1.04, the Hausdorff dimension of the pin distance set is at least basically 0.6904. Okay. So this is where we're at. Okay, I never said this, but everything that I'm talking about, all the sets here are analytic, and this is necessary. So everything in here is a planar analytic set. Okay. So using effective dimension, we can improve these bounds, at least when the dimension of E is closer to 1. So something I proved July is that if E is an analytic set in the plane, the Hausdorff dimension of this set is strictly greater than 1. Then for all points outside a set of Hausdorff dimension at most 1, the pin distance set of E with respect to X is at least the dimension of the set E divided by 4 plus 1/2. And so this is going to give the best known bounds when the dimension of E is close to 1. So as the dimension of E is getting closer to 1, the right hand side here is getting closer to 3/4. We're improving on the bound, Schmerken's bound of 0.69. Oh, yeah.
When you say outside of federal Hausdorff dimension, instead you federal dimension of one from your origin set.
So I'm saying that any set, sorry, the set of points which don't satisfy this has a Hausdorff dimension of 1, of at most 1. So it's a small set.
Is this the same as saying that you're considering like a smaller set?
It's inside E, but outside this. So it's excluding some points.
No, I'm asking whether it's the same thing that the original E is like.
I'm saying that if
Even E, there's like E half containing E such that. Okay, is it the same?
there's a subset of E of bad points, and it's a negligible subset.
No, let me try. Take the bad points, move them from E. Have you caught your tail already, or do you have to?
Yeah, so if you remove the set of bad points, the dimension doesn't change. So
And the dimension of these things.
Right.
The dimension of E doesn't change, and then the rest of it is true as well.
yes.
That's what you're saying.
Yeah. Yeah, so the restriction on the dimension here is at most 1. It means if you remove them, nothing changes. The size is the exact same. Okay. All right, so we're going to prove this theorem using effective methods. And when you do this, kind of the first step is to reduce the classical result to a pointwise result. So here's the pointwise analog that we're going to actually prove. The first instances of using effective methods to yeah, so in the first instances of using algorithmic techniques in the context of geometric measure theory, this reduction was very easy. Essentially, you have a pointwise analog, and then you just appeal to the point acceptance. And just remember to write an oracle on your theorem. Okay. But as we did this more and more, the reductions became harder and harder. And so this actually is not an easy reduction from the classical statement, this, to the pointwise statement. The main ingredients are a theorem of Orpington on radial projections combined with the point to set principle, but this is, I think, I won't have time for this. So I'm going to take this reduction as a given and just tell you that if we can prove this theorem, then we prove the classical result. The second thing I want to say is I'm going to simplify the exposition by just trying to lower bound the pin distance set by 3/4. So this is just a simplification. If you understand how we do this for 3/4, it's not too bad to recover the full result. Okay, so this is our pointwise analog, and this is what we're going to show. So if we have 2 points in the plane, x and y, and we set the direction from x to y as E1, and we require that these things satisfy the following conditions. So the dimension, the effective dimension, and the effective dimension of y are strictly greater than 1. The complexity of E1 relative to x is essentially maximal. So if x is random relative to, if the direction E1 is random relative to x, we also require y to be independent of x, which means x contains no information about y. And then we require y to contain no information about the direction. So we want the complexity of x and y and e to be large, and we want them all to be independent of each other. So no two things contain any information about each other. So this is a very strong condition, and that's why the reduction requires some work.
Can you explain the difference between P2 and C4? The way in which it was on X and Y, not know about it?
Yeah, so a technical condition, I could get away with doing this at C2, but I have to restrict to a conditional here because I don't have enough control over Y. So I had enough control over X to require this, but not for Y.
And little o.
Little o, so just a sublinear.
Oh, yeah, okay. So this is, so C4 is just a much weaker set than C2.
Exactly. Mhm.
And what you're saying is the first part of it's implied, don't know much about the first V1, sorry, part of it's V1, but they can know more than log.
Yeah, more than log, just some sublinear. You can actually replace this with log, I think, but ultimately it doesn't really matter. As long as these things are sublinear, everything's okay. But you want to think of this as just X, Y, and the direction E don't contain any information about each other. They're independent.
Able to get these points in your analytic set.
Yeah. So that's very surprising. And the way you do that is through a classical theorem by Orpington.
A classical theorem tells you how many points.
So you're going from the classical statement. We use a classical theorem to get the points we want to do this reduction, prove this theorem, and then go back through the point to set principle. But yeah, so this is a more complicated reduction than.
So the steering below, right, objective is telling you really use these points, right?
Yeah.
Just unpack the point to set principle.
Basically, yeah. There's a bit more work. You can't just immediately apply radial projections and conclude everything, but yes, that's more or less. Okay. All right, so we're going to focus on proving this theorem. Okay. So we're going to fix these points x and y, which satisfy the 4 conditions, the independence that we need. And we want to prove that the effective dimension of the distance between x and y relative to x is at least 3/4. So because of the way effective dimension is defined, kind of the most natural thing to do is fix a precision and prove the corresponding lower bound at that precision, and then take a limit inferior. So we were going to fix a precision r, and we want to show that the complexity of the distance between x and y at precision r is at least roughly 3/4 times r. By the symmetry of information, this lower bound is equivalent to an upper bound on the complexity of y given the distance between x and y. So I want to prove a lower bound on the complexity of the distance between x and y, which is equivalent to proving an upper bound on the complexity of y given the distance. So if you think about this for a bit, this is the amount of information needed to compute y if you know x and you know the distance between x and y. So from a computer's point of view, it knows x and it knows this annulus around x. And it's trying to find y. So you're trying to find this point y in the annulus. So what we want to do is bound the number of z's, the number of points z, or the size of the set of z's, which have the same distance from x as y does, and whose complexity is at most y. So this is our goal. We want to bound the set of z's contained in this annulus of small complexity. So up till now, so kind of the first real step of the game is to reduce this to a theorem about projections. So if you have a direction, so a unit vector in the plane, and you have a point x in the plane, the projection of x onto E is just the dot product. So it's essentially the orthogonal projection of x onto the line passing through the origin in the direction B. Okay. So that's, we're going to label that PE of x. We want to reduce our goal of bounding the set of points on this circle to projections. The reason we want to do this, the reason this is a sort of natural thing to do, is that projections are very well or much better understood. And they're very nice. They're linear and they have all these nice properties. So if we can do this, then our lives are a lot easier. So the reason projections actually come into play here, there's actually two reasons. So suppose that Z is a point on this circle, so its distance from x is the same as the distance as y from x. There are two projections. The first is that if you project Z onto E1, which is the vector from x to y, so if you project Z onto this line, it will be very close to the projection of y onto that vector. Okay. So the projection of y is very close to the projection of Z onto E1. The second way projections come into play is that if you take the midpoint bisector W between Z and Y, it has the exact same projection as X if you're talking about E2. So the main goal of this, our main goal here, we're going to be using a divide and conquer strategy. We're going to use this idea, this bound, to bound the set of points C which are far away from Y. We're going to use the second equality to bound the set of points which are close to Y. It's divide and conquer. Using one, we get a pretty weak lower bound on the complexity of the distance. Using one, we only get that the complexity of the distance is at most, or at least, half of the complexity of y. So this is a pretty weak bound, which is good when the complexity of y is large. So we're going to leverage that in the following way. When z is far away from Y, we use 1 and we get this weak bound. And then we're going to use the second equality to bound the points Z which are close to Y. And it's an optimization problem, and I'll just tell you the answer. The appropriate T to choose, the appropriate distinction on what's close and what's far is the precision which causes at which Y has complexity about R over 2. In other words, we're going to choose T so that the complexity of Y is roughly R over 2. Okay, so if you plug this in to this bound here, we see that at that precision T, the complexity of the distance between X and Y is about R over 4. Okay, so all of this, I'm not going to tell you why this is all true, and now I'm going to attempt to show you what's going on in this second case, and this is actually where most of the technical improvements are. Okay. Okay, so we fixed an appropriate T. We gave a lower bound of the complexity of the distance between X and Y at that precision. And now we need to show that that the complexity of the distance from that point on is what we need it to be. Okay.
Top line, complexity, R, how many?
Yes, so we want to show, so we've showed that the T bit, the first T bits of the distance is at least R over 4.
That's between R and T.
And we need to show that the remaining R minus T bits have complexity R over 2. So if we have those two things, we can combine them to get a lower bound of 3/4, which is what we want. So okay, so using some symmetry of information, and if you haven't seen this before, it's probably going to move too fast. But if we want to prove a lower bound on the remaining R minus T bits of the distance, really what we need to do is show that the number of bits required to compute Y, if you know the distance, so you have this circle, and you know the first T bits of Y is small. So we just need to bound the number of bits required to compute Y, so to compute the point on this circle. If you already know X, you know the distance, and you know some neighborhood of Y. This is where we use the second projection equality, where we use the fact that the midpoint W between any two points on the circle has the same projection as X. Okay. To see why this is useful, notice that if you know Y and you know Z, then you know W. So if you know Y and Z, you know W, and you know this line, which contains X. So if you know this line, which contains X, to compute X, all you need to know is the position of X on that line. This is exactly what I mean by a projection theorem. I want to bound the number of bits required to compute X if I know the line it lies on. So I'm turning this question into a projection theorem, a question of how difficult is it to compute X if I know a line that it lies on. Okay, so that's exactly the first sentence of this slide. We want to bound the complexity of computing an approximation of our point given its projection and given the direction. In other words, given the line, I want to know where X is on that line. How hard is it to compute X if I know the line that it's on? So this is a really well-studied problem. And when the direction of E is random relative to X, when the complexity of E given X is about R, we have a tight bound. We know that the complexity of computing an approximation of X, given the projection of X and given the direction, is the least that it can be. The complexity of X minus R. This is a tight bound, and this is the pointwise analog of Marstrand's projection theorem. This is something that Neil Lutz and I worked out a couple of years ago. So unfortunately for our application with distances, we don't have enough control over the direction to directly apply this result. If you go back to here, we're looking at this direction. Sorry, we're looking at this direction, E2. We have very little control over E2. However, we do know something about it. We do know that the direction is random up to a certain point. So it has an a high initial complexity. After this point, after some precision, it could be totally non-random. But at least for the first S bits, it is random, or S is equal to the distance between X and or Z and Y. Okay. So we want to use this property to get an upper a good enough upper bound on the complexity of computing X. Okay, and so this is the content of really the main theorem of this paper. The distance result. This is where most of the technical improvements are in the paper. Okay, so I showed that if you have a point in the plane whose dimension is big, is at least 1, you have a direction E, and you have 2 precisions R and T. And you suppose that the complexity of the direction given X is about T. So in other words, T is random conditioned to X, at least up to precision T. And the complexity of computing X, if you know its projection and you know E, is at most the complexity of X at precision R minus R plus T. So a couple, So just a couple comments on this. This really is a generalization of the pointwise analog of Marstrand theorem. So when T is equal to R, this becomes the complexity of X at precision R minus R. So this is, we recover the Marstrand projection theorem when we assume that E is random with respect to X. And in this case, the bound is tight. When T is much smaller than R, so as we know, the direction is not as random as we would hope, it's likely that this bound is not tight. We should be able to do better than this, but I'm not sure how. But if we were able to do better than this, it would almost certainly lead to improvements on the distance set problem. So if you could improve these bounds even by a little bit, these should correspond, these should translate to improvements on the distance set problem. Any 320?
Yes, with that.
Okay.
Fundamental spots.
Okay.
And give it a little coffee.
Okay. All right. So I guess I'll give just a brief some of the ideas that go into this proof. Okay, so the basic idea is to generalize the known projection theorems to intervals. And so if you take a point X in the plane and two precisions B and A, we say that the interval AB is teal if the complexity of X at precision B given X to precision S. In other words, if the complexity between the bits, the first S bits of X and the first B bits of X is less than B minus S, then this interval is teal. Another way to think of this is more geometrically. If you look at the complexity function as a graph, so you just graph this, the complexity function of X, and you look at, and you draw a line with slope 1 emanating from the complexity of X at precision B. If the graph is below this line from S to B, then it's teal. We say that an interval is yellow if you draw the line of slope 1 emanating from the complexity of X at precision A, and the graph is entirely above this line, then it's yellow. And so we have these two types of intervals. And if you just look at the proof from Neil and my paper, you'll almost immediately be able to generalize projection theorem to work when the intervals are teal and when the intervals are yellow. And so the proof of this theorem is really trying to cut up the interval from 0 to R so that you can sum up the bounds that we get from the yellow and teal intervals. The issue is that the naive partition does not necessarily work, and it actually would fail badly if you tried to just greedily cut it up into yellow and teal intervals. For the simple fact that you might have too many yellow intervals, which cause the complexity of this to be too high. Nevertheless, you can slightly optimize. So this isn't a dramatic optimization. You just kind of have to not be the most naive, and you get the contribution that's needed for this proof. I'm not certain that I don't think that that this part of the proof is amenable to improvements. I mean, I'm sure you can do some improvements here, but I'm not sure that in general you can find a better partition that would dramatically increase the distance set bound. I really do think the best thing to do is try to prove this, to increase this bound in a different way, I guess what I'm saying. Okay. So let me just finish by saying that once you know this bound, the rest of the proof is plugging this into the idea here and using some symmetry of information arguments. And what pops out is that you bound the number of points Z, which are very close to Y. Okay, so I'm not going to really go into that, but I just want to say that this bound pretty much does what you want, and the rest of the proof goes more or less smoothly. Okay, thank you.
Any other questions? Very complex geometry, back and forth, it seems like.
Yeah, it's, yeah. Okay.
Complex. Any others? So,
Can we ask questions from the Zoom chat?
Sure.
Oh,
ahead.
okay, great. I just had kind of a basic question about kind of the definition of this Housework Dimension point to set principle, where you're taking the minimum of all oracles. I'm coming at this more from a geometric measure theory background than a logic background, but what does the oracle help you with here? Like, it seems like if the oracle is too good, then it could kind of do all the work for you. So how does this oracle limit how easy it is to get this dimension?
And then part two would be that.
Oh, yeah, so what this oracle is doing is essentially encoding a sequence of covers of your set, which converge to optimal.
Sequence of covers.
So if you take
Oh, right, yes.
If you take the classical definition of Housework Dimension, you get the sequence of covers that converge to the right value. If you encode all those into your oracle,
Right.
you get the minimum.
That's interesting. So the oracle kind of tells you which of the sets in your cover you lie in, or something like this.
Yeah. So the effective dimension is, how hard is it to specify, your point to precision 2 to the negative r, and you look at that. You look at the limit inferior of that. And so if your cover, if the cover is very small, then there aren't that many covers to specify. There aren't that many sets to specify if you want to specify x to precision 2 to the negative r, for example. So you get a very low dimension point.
All right, that makes sense. Thanks. That helps.
So are there other questions online? I can't see online people, so just speak up. Other questions, you're welcome. All right, let's thank the speaker. Isabel's going to tell us where to get your coffee.
Yes, I don't know what happened to our coffee.